Hi everyone. In this video, we are going to be solving the ordinary differential equation for the undamped and the damped simple harmonic motion. So before you start watching this video, I would recommend watching the video where we derive the general forms of second order linear differential equations for all the three cases. The video will be linked in the top right of your screen, but we are going to be using the general forms of those solutions in this video today. So, as we mentioned in that video, differential equations are used widely to represent physical situations, and one of them that we're going to be discussing is the simple harmonic motion. So here we have a simple harmonic oscillator, which is a mass tied to a wall with a spring. And what how the system will behave is that it will oscillate back and forth as the spring compresses and stretches. And so we want to derive the equation of motion of this block based on the force that we know that the spring will exert on the block. So we know that the force that the spring will exert on the block can be written as in the form of F is equal to minus kx, where k is the spring constant of the spring and x is the displacement of this mass from its initial position. So here the mass is, or rather its equilibrium position. So here the mass is its in equilibrium position, and the more the mass moves from its equilibrium position, the higher the spring will be stretched or compressed depending on which side it moves, and the higher force it will exert on the block. So this is a force that we have, that is F is equal to minus kx, that will be acted on by the spring. Now from Newton's second law, we can write that the force that will be exerted on the object can be written in the form of F is equal to ma, that is also equal to minus kx. And we know that the acceleration of the object can also be written as a second order derivative of the position of the object. And taking all the equations on one side, we get the following form. And then we do one more step, which is dividing both sides of the equation by the mass. So it cancels out from the first term. From the second term, we have this. So this is a differential equation of a undamped simple harmonic oscillator. And solving this differential equation will give us a function of x such that it will describe the displacement of this mass from its equilibrium position. So let's do that. Let's solve this differential equation. So we'll make one more substitution here. That is in the second term, we'll write omega square x instead of k over m, and we are writing omega square instead of k over m, and we just do this because it makes our calculations a little easier. But so now we have our second order differential equation. This is often written in this form as well. There will be x double dot plus omega square x is equal to 0. The double dots here indicate the second time derivative of x with respect to time. So when we want to solve this differential equation, so let's just write down. We are solving the differential equation. So as we can see here that the second order derivative term will be replaced by d square. The omega square will be as it is, and instead of x we'll write nothing, and this will be equal to 0. So if you're unfamiliar with what we did here, again I recommend you check out the previous video. Will be linked in top right of the screen. But essentially what we do is we replace the second order derivative with a d square term, and then the term which has no time derivative, we just remove it from the equation. And so this quadratic equation can be written in the following form. D plus I omega and D minus I omega is equal to 0. So this is, we are breaking this equation down into the form of a plus b and in a minus b. So when you multiply these two, you'll get a square minus b square. So the a square term will be d square, and the b square term will be iota square omega square, and iota square would be equal to -1, and negative of -1 would give us a positive sign. So that is all we've done here. We've broken this equation down into two parts, and so now we know that the solution of this equation will be plus or minus I omega. So this equation, this ordinary differential equation, is of the third type where the roots of the equation are imaginary, and we know that when we compare it with the equation of the form of a plus ib, this will give us a as equal to 0 and b as equal to omega. And we know the general form of the solution of when the roots are imaginary and complex conjugates is of the form x is equal to e raised to at c1 cos bt plus c2 sin bt. Again, please refer to the previous video for to know how we got this general form. But for now, we know that the value of a is equal to 0. So that'll just give us 1 on the outside, and the value of b is omega. So we have c1 cos omega t plus c2 sin omega t. Now we can leave the general, and I'll just open up the bracket since it just clutters up the solution. We can leave the solution as it is, but what we'll do here is we'll now get this equation, we'll convert this equation to the general form of the simple harmonic oscillator, which is of the form we used normally, which is a sine omega t plus phi. In this form, we know that A is the amplitude of the simple harmonic oscillator and phi is the phase or the initial phase of the simple harmonic oscillator. So we want to get from here to here. So the way we go about doing that is making a couple of substitutions. So we make the following substitutions. We say C1 is equal to A sine phi and C2 is equal to A cos phi. So essentially what we are doing here is we have two unknown constants C1 and C2, and instead of writing C1 and C2 we'll write them in the form of A and phi, or as functions of A and phi. And this is because we are more familiar with A and phi as physical quantities, and that writing the solution in the general form that has A and phi is more convenient. So let us substitute the value of C1 and C2. So we have A sine phi cos omega t plus A cos phi sin omega t. And using a trigonometric identity, we can write this equation in the form of A sine omega t plus phi. So we now have converted the general form of the solution that contains C1 and C2 in the form of A and that contain in the form of the solution that contains A and phi. One more exercise that is helpful here is determining A and phi in terms of C1 and C2. So we'll just do that right here. The value of A will be equal to square root of C1 square over C2 square. And we can check this if we place a value of C1 square as A square sine square phi and C2 square as A square cos square phi. The A square would come out common of the square root, and then it would just be A. The sine square phi plus the cos square phi would be equal to 1, and I would encourage you to do this for yourself. And similarly for phi, we would have the relation of phi is equal to tan inverse of C1 over C2. And again, this is also pretty simple. You divide C1 by C2 and you'll get tan phi, and you take the inverse tangent and you get phi is equal to tan inverse C1 over C2. So we know now, given a differential equation and some initial conditions, we can determine C1 and C2. Then once we know C1 and C2, we can determine the amplitude and the phase of the harmonic oscillator, and we can determine the general form of the simple harmonic oscillator. So uh, the way a simple harmonic oscillator works, I'll show this in a graph right here. It is as follows. So the trajectory of the simple harmonic oscillator is shown by this blue solid line. So as we usually know, the oscillator will go back and forth about its mean position, which is indicated by the dashed orange line. I'll keep on doing so forever since there is no damping in the system. And this is how a simple harmonic oscillator works. And we now know how to solve the differential equation for a simple harmonic oscillator. So now let us start with the damped simple harmonic oscillator. So we are now starting with the damped simple harmonic oscillator, damped simple harmonic oscillator, and we will solve the differential equation for the damped simple harmonic oscillator. But let's see what a damped simple harmonic oscillator is. So this is a damped simple harmonic oscillator, and the only distinction it has from the normal harmonic oscillator is that there is a damper in the system. Now what will damper will do is that it will prevent, or it will try to slow down the oscillation of the harmonic oscillator. Such dampers are often used in door knob excuse me, door hinges, where you want to slow the door down and not make it crash with the wall, and they are often used in a lot in different mechanical systems, just so that the system cannot oscillate very fast and we can control the rate at which the system oscillates. So the equation of force that we can write here is that the spring will have a restoring force of minus kx, and the damper will have a force that is equal to minus bv. Here b is a proportionality constant, and the way these dampers work generally is that the damping force is proportional to the velocity of the object or of the oscillator. So let us just write that down here. So f here is proportional to the velocity, or the damping force is proportional to the velocity, and we often indicate by a subscript of b. But the faster the object oscillates, the stronger the damping force, and the slower it oscillates, the weaker the damping force. Again, from Newton's second law, we can write F is equal to ma, and that is equal to minus kx minus bv. So let us rearrange the equation in the following way. We'll take all the terms on one side of the equation. Now we know that the acceleration is equal to the second time derivative of the motion of the object. So let's make that substitution. We write, instead of acceleration, we write t square x over dt square. The velocity is equal to the first time derivative of the position, and the kx term will be as it is. So this is our differential equation. Let's solve this differential equation now. So solving the differential equation. So the second order derivative term here will be written as d square. So let's do that. We have m d square plus b. The first order derivative will be just d, and the no derivative term will not be written in this equation. So this is a quadratic equation whose roots we want to find. So let's use the discriminant method, and we can write the roots as d is equal to minus of b uh, plus or minus square root of b square minus 4mk over 2m. So we'll make a substitution here, and let's write down. We'll make a substitution. We'll call the value of omega d square, a new variable, as equal to the square root of b square minus 4mk, and we'll take the modulus of this, and I'll explain why, over 2a. And this is the value of omega d, and the reason we've done this is because we want omega d to be the damped frequency of the oscillator, and the frequency of the oscillator can only be positive. So what we're doing here is that we are taking the modulus of this term, which can be negative depending on the value of m and k and b, and we'll just take the modulus so that the frequency will always be positive, and any other negative terms we'll handle in the equation itself, and we'll see how. So the actual value of this square root though will depend on the values of b, m and k. Now b, m and k are all known quantities to us. The damping constant of the damper b is known to us, the spring constant k is known to us, and the mass of the object m is also known to us. So these are all quantities that we know experimentally, and all we want to determine is the function x, the value of x as a function of time. So now that we know omega d, will be breaking the solution down into three cases. So if you recall the previous video, uh, the solutions of this quadratic equation can be real and distinct. They can be imaginary and complex conjugate, or they can be the same. So it all depends on this quadratic equation. So let us start with the first case. In the first case, we have b square, the value of b square is greater than 4mk. And this case is also known as the overdamped case. And we'll see why. So when we have b square is greater than 4mk, so the term inside the square root right here will be positive, and hence the square root will be real, or the value of the square root will be real, and the roots that will obtain will both be real and distinct. So the solution in this case would be equal to x is equal to c1 e raised to r1t plus C2 e raised to R2t. And here R1 and R2 are, as we know, the roots of this equation. So uh, R1 and R2 are the roots of this equation right here. So let's just write that down. We have R1 and R2 are values of this equation or of this solution. So knowing the values of B, M, and K, since they are all practically known to us, we can determine the value of R1 and R2. And then we know R1 and R2, and C1 and C2 will be determined by the initial condition. So let's do an example for this case. So we have been given a differential equation of x double dot plus 4x dot plus 3x is equal to 0. And we also know the initial conditions, x of 0 is equal to 1 and x dot of 0 is equal to 0. So we want to solve this differential equation. We write the second order derivative as t square, first order derivative as t. The no derivative term stays as it is, and for the quadratic equation, we have the roots of the equation as r1 and r2 will be equal to -1 and -3 respectively, and you can solve the quadratic equation and find it out for yourself. And so the general form of the equation will be equal to x is equal to c1 e raised to minus t plus c2 e raised to minus 3t. And to determine the value of c1 and c2, what we do is we place the value of x is equal to 0, and we determine one equation for c1 and c2 with that, and we then place x dot as 0 and determine another equation. And uh, finally, when you do all of that, you get the value of c1 and c2 as 3 by 2 e raised to minus t, and c2 will be equal to minus 1 by 2 e raised to minus 3t. Again, I would recommend you watch the other video that we did on differential equations on to determine how to know how we find the value of these constants. But now that we have the equation of motion, you can see that there are no trigonometric terms in this solution. So it won't really oscillate. So how does the graph of this oscillator look like? So let's see the graph. So the graph of the oscillator will be as follows. So as usual, we have time on the time on the x-axis, the displacement of the oscillator on the y-axis. The mean position of the particle will be at 0, indicated by the orange dashed line. So now we can see that the oscillator starts at an initial position of 1, which we had right here. The initial position of the particle was 1. So it starts at 1, but it just goes to 0. It doesn't oscillate any where, and this was very evident from the solution of the equation that we got here. So both the functions of time are exponentially decaying functions, and as a result the displacement will just exponentially decay to 0, and the decay will be controlled by the weaker exponential, that is this term right here. And the reason we call this the overdamped case, so we mentioned this was the overdamped case when b square was greater than 4mk. So that is because the damper is so strong that it does not let the mass oscillate. It will directly stop the mass before letting it complete an oscillation. So this is the overdamped case that we have. So now let's do the second case. The second case that we have is b square is equal to 4mk, and this is called critically damped. Now, when b square is equal to 4mk, what do we have here in this in our root? So when b square is equal to 4mk, this term will just be 0. So we just have one unique root which will be equal to minus b over 2m. So in this case, the general form of the solution when we only have one root, excuse me, will be of the form c1 e raised to minus rt plus c2, and then we multiply the second root with a t, and again e raised to minus rt, and here r will be equal to minus b over 2m. And again, this is similar to the case where we only have one distinct root. And when we have only one distinct root, we multiply the second term by t to get uh, two distinct roots. And this is the general form of the solution then. And we often write it in the following form as c1 plus c2t into e raised to minus rt, and this will be the general form of the critically damped case. So let's understand it with an example again. So the example we have is x double dot plus 4x dot plus 4 is equal to 0 with the initial conditions x of 0 is equal to 1 and x dot of 0 is equal to 0. So now when we solve this case, what do we when we solve the differential equation, the general form of the solution will come out as x is equal to e raised to minus 2t 1 plus 2t, uh, and I've directly written the solution, but I would highly recommend you solve the differential equation, find the general for solution, and then you find the value of the constant c1 and c2 from the initial conditions. But this is the answer that we get. So again, this you can see in this equation that we have a exponentially decaying term and then we have a linear term. So let's plot this general solution. So the graph of displacement versus time for this case looks as follows. So again, the exponential term is the one that dominates the behavior of this oscillator, and we can see that similar to the overdamped case, the displacement of the particles gradually goes to 0. However, in this time, it goes approaches 0 more quickly. But the special case about the critically damped case is that if the damper was any weaker or if the spring was any stronger, you would the particle would start oscillating, and that is why we call it the critically damped case, is because beyond this point the we'll see oscillations, and that is in the case in which we see oscillations. That case is called the underdamped case, where we have b square is less than 4mk, and this is the underdamped case. So underdamped case, and now when we have b square is less than 4mk, in the roots of this equation right here, the value of b square minus 4mk will be negative. So the roots will be real and imaginary, and so the roots in this case will be real and imaginary, and hence the general form of the solution will be of the form e raised to at c1 cos bt plus c2 sin bt, and a and b in this case. So to know a and b, we know that our roots here r1 and r2 will be of the form, so r1 and r2 can again be determined right here. So the value of b square minus 4mk over 2m, or square root of b square minus 4mk over 2m, we know is equal to omega d. So the roots of the equation will be equal to minus b over 2m plus or minus I omega d. And so when we compare it with a plus ib, we know that the value of a will be equal to minus b over 2m, and the value of b will be equal to omega d. So the general form will be equal to x is equal to e raised to minus b t over 2m c1 cos omega dt plus c2 sin omega dt. And similar to the undamped harmonic oscillator case, we can again write C1 and C2 and omega d in terms of A and phi. So we have A e raised to minus bt over 2m sine omega dt plus phi. And again, what we've done is instead of C1 and C2, we've used two other variables A and phi, and we already know how to write A and phi in terms of C1 and C2. So let's do an example for the following case. Before doing the example, we'll notice that in the general solution, we can see that there is a trigonometric term, a sinusoidal term, which shows that the particle will oscillate. But then there's also an exponentially decaying term, which indicates that the particle will slowly decay its amplitude. So let's just understand that with an example. The example that we have here is x double dot plus 2x dot plus 10x is equal to 0 with the initial conditions x of 0 is equal to 3 over 4 and x dot of 0 is equal to 0. Now again for this case the roots will be real and complex conjugates. So the general form will be equal to the solution rather will be equal to e raised to minus t 3 by 4 cos 3t plus 1 by 4 sine 3t. And again, I would encourage you to solve the differential equation, find the general solution, use the initial conditions to determine the values of C1 and C2. But the plot of this solution is as follows. We can see that the particle will oscillate a couple of times, but the amplitude of the oscillation gradually decreases and eventually the particle stops oscillating. So this kind of a setup is often used in doors that will oscillate about their closed position of a couple of times before coming to a stop. And the reason this is called underdamped is because the damper is weak enough. It cannot is weak enough to not stop the oscillation of the particle, but it will eventually slow down the oscillation, and the particle will eventually come to a rest. So the trigonometric terms are what give rise to the oscillation of the particle, while the exponentially decaying term is what decreases the amplitude of the oscillation. So we have now dealt with all the three cases of the damped harmonic oscillator as well as the undamped harmonic oscillator, and we have seen how to use differential equations and how to solve these differential equations to determine how these oscillators will behave under different conditions. So that's all I'll cover in this video. If you like the video, please give it a like. If you have any doubts or recommendations, please leave them in the comments down below. And thank you for listening.